Hello everyone, welcome to this video on rough set theory part 1. In this video I will discuss about information system, indiscernibility and set approximations. The concepts like redact and core, discernibility matrices and functions, rough membership and similar concepts will be discussed in my future video. Rough set theory was first developed by Pawlak in early 1980s. The main goal of rough set theory analysis is to synthesize approximation of concepts from acquired data. It is a new mathematical tool to deal with vagueness and uncertainty. Rough set theory has a wide variety of applications in the field of artificial intelligence, machine learning, data mining, knowledge discovery and from databases, and so on. Now let us see what is an information system. An information system is a collection of objects or entities in which each object is described in terms of some features or attributes. Each row represents an object or a case or an entity, and each column represents an attribute, and corresponding to each object and corresponding to an object and an attribute, there is a value associated with it. Let us see an example. We have a patient table here. The table has 5 patients or 5 objects, and each patient is described with respect to 2 features or attributes. These are age and limbs, and corresponding to each object and an attribute, there is a value associated with it. For example, the patient X1 has age 16 to 30, patient X5 has LEMS score of 26 to 49. So such tables are called information systems. And an information system is a pair of UA, where U is a finite non-empty set of objects and A is a finite non-empty set of attributes. The elements of A are called the conditional attributes. So here in this case, U consists of X1, X2, X3, X4 and X5, the collection of all the objects, and A is the collection of all the attributes. These are called conditional attributes. Now given this information system, if we add one more attribute, which is known as a decision attribute. Here we have added the work attribute, which we call a decision attribute. Now this information system has turned to a decision system. So an information system with conditional attributes and decision attribute is called a decision system. An information system is also known as a decision system when it contains one or more special attribute called decision attribute. And this special attribute is not from the conditional attributes, and it is defined as a pair of U, A union D, where D does not belongs to A. In this example, the decision attribute is work, which has 2 types of values, yes and no. Next is indiscernibility relation. Indiscernible means indistinguishable, means inseparable. Now 2 objects are inseparable if they have same value for a particular attribute. So let us see the example first. Here object X1, object X2, object X6, they have same value for the attribute age 16 to 30. So they will form a single group and they will form one indiscernibility relation. So here X1, X2 and X6 will fall to the first indiscernibility relation or first group. Next, X3 and X4, these 2 have same value with respect to attribute age, so it will form the second group. And object X5 and X7, X5 and X7, they are same with respect to the age attribute, because both of them have 46 to 60 as their value, so it will form the third group. So this is the indiscernibility relation with respect to age attribute. So we can compute indiscernibility relation with respect to each attribute or with respect to all the attributes. Similarly, we can compute indiscernibility relation with respect to the length attribute, and it is actually the indiscernibility relation is denoted as ind of the name of the attribute. Now with respect to the length attribute, we can see, if we think about all the lengths, so first object x1, the score is 50. Is there any other 50 in this column? No. So this is the first indiscernibility relation, or the first group, and it has only one object because no other object has 50 as length score. And next x2, the score is 50, sorry, the score is 0, and there is no other object with 0 as length score. So this is the second group. And similarly x3 and x4, you can see here x3 and x4 have same value for lengths. So this is the third group. And similarly x5, x6 and x7 have same value, so they will form the final group. So this is the indiscernibility relation with respect to length attribute. Now two attributes together, or all the attributes together. So see here, if we think about both length and age together, so for object x1, the pair of value is 16 to 30 and 50. Now is there any other same pair of values? We don't have. So that means with respect to length and age, x1 will fall to the first group, and this is the the first group will have only one object because there is no other object with same pair of values. Okay, so this is the first group. Similarly x2 has 0 and 16 to 30, so and x2 will form the second group. x3 and x4 have same pair of values, and there is no other object with the same pair of value, 31 to 45 and 1 to 25. So x3 and x4 will form another group. And similarly x5 and x7, if you see x5 and x7, they are also having the same pair of values. So this is the next group, and x6 is left with this pair of value, and there is no other object with the exact same pair of value. So x6 will be the last group, and this is the indiscernibility relation with respect to age and lengths. So for an information system S equals to UA with B subset of A, there is associated an equivalence relation denoted as ind of B, and ind of B is equals to x dash belongs to U square, such that for all A belongs to B, A of x is equals to A of x dash. A of x is equals to A of x dash means two different objects x and x dash, if they have same pair of values with respect to the attribute A, then they will fall to the same indiscernibility relation. Okay, so this is all about indiscernibility relation. Next is set approximation. So let us take the equivalent classes once again. The equivalent classes are also known as indiscernibility relations. Okay, so these are our indiscernibility relations. We have here 1, 2, 3, 4 and 5 indiscernibility relations, or these are also known as equivalent classes. Now can we find a set of equivalent classes such that each object belong to yes class? Okay, we are going to make a set, okay, of equivalent classes such that each object belong to yes class. Okay, so let us try with the first equivalent class. Here x5, x7. So here you can see x5 belongs to no class x7 belongs to no class. That means none of them belongs to yes class. Okay, so this is not included in the set. Okay, so we have here yes and no, these two type of classes we have in the table, in the information system. Next, x1, the next equivalent class is x1. So x1 belongs to yes class, so it is part of the set because each object belongs to yes class. This condition is fulfilled by this particular equivalent class. Next, x2 belongs to no class, so it is not included in the set. x6, yes, it belongs to yes category, and that is the reason that it is part of the set. Next, x3, x4, this equivalent class, let us see in which class they belong. x3 belongs to no class, x4 falls in yes class. So both of them do not belong to yes, even though one of the object belong to yes class, but the other one, the x3 is do not fall in yes class. So the condition is that each of the object should belong to yes class. So the condition is not fulfilled, and this is the reason that this is not included in the set. Okay, so the set formed in this manner, okay, is actually called the lower approximation, and it is denoted as b lower bar x. Here b represents actually the set of conditional attributes age and lambs, and x represents the object belonging to yes class. Okay, here x represents the object belonging to yes class. Next, we are going to form another set. Okay, the set of equivalent classes such that one or more object belong to yes class, or at least one object belong to yes class. Suppose here we have two objects, so if at least one object belong to yes class, we are going to take both the objects in the set. Now here in the first equivalent class x5, x7, so we have already seen none of them belong to yes class, so it is not included in the set. x1 belongs to yes class, so it is included here. x2 is in no class, so it is not included because we need at least one object to be in yes class. x6 again in yes class, so it is part of the set. Now x3, x4, here if you see carefully, x4 belongs to yes class, but x3 do not. x3 is in no class, but at least one of them is in yes class. So this fulfills my criteria. At least one of the object belongs to yes class, and that is the reason that x3, x4 is part of this set. So the set formed in this manner is called the upper approximation, and it is represented as b upper bar x. Next, boundary region. So here simply the upper approximation minus lower approximation will give us the boundary region. So we'll see all these concepts, all these approximation through an example in detail. The various approximations are defined here. So for information system S equals to UA with the B subset of A and X subset of U, we can approximate X as follows. And the equivalent classes are denoted using XB. The lower approximation is equals to X such that XB is subset of X. If XB intersection X not equal to null, then we have the upper approximation. The boundary region is defined as B upper bar X minus B lower bar X, that is upper approximation minus lower approximation. B outside region is defined as U minus B upper bar X, that is universe minus the upper approximation. Each of these definitions will be more clear when we will discuss with an example. So let us see an example. In this example, we are going to approximate a set W, which is defined as X such that walk of X equals to yes. That means the set W is going to be like this. The set W has those objects whose decisions are yes. Okay, so this is the meaning of this definition, and we are going to approximate W with respect to B, and B has two attributes, age and length. That means we are going to approximate W with respect to both the conditional attributes. Now let us see the solution. So first, in step 1, we need to compute all the equivalent classes, or what we know as indiscernibility relations. So these are all the indiscernibility relations which we have seen earlier, and this is the set W. Now let us see how to compute the lower approximation. So the definition of lower approximation is here. That is, if an equivalent class is subset of W, then all the members of that equivalent class will be part of the lower approximation. Okay, I repeat, if all the members of an equivalent class or the equivalent class is a subset of W. Now here the first equivalent class is X1. So is X1 a subset of W? This is the definition. If the equivalent class is subset of W, then it is a member of lower approximation. So here X1 is subset of W. Yes, so X1 comes here. Next, X2, the next equivalent class. Is it subset of W? No, because we don't have X2 here. So X2 is not included in the lower approximation. Next, X3 and X4, or this particular equivalent class. Is it subset of W? No, because we don't have X3 in W. We have X3 here, we don't have X3 in W. So this set, this equivalent class is not included in the lower approximation. Next indecendability relation is X5, X7. So is it subset of W? No, again. Okay, so it is not included here in the lower approximation. The last one is X6. Is it a subset of W? Yes. So X6 is taken in the lower approximation. So this is how we compute the lower approximation. Next, let us see how to compute the upper approximation. Here the condition is, if the equivalent class intersection the set W is not equals to null. That means if there is something common in XB and W, then all the objects will be part of upper approximation. Okay, so here the first equivalent class X1. So X1 intersection W, because here the equivalent class intersection W. So X1 intersection W. Is there anything common? Yes, we have X1 here and X1 here. So X1 will come as a member of the upper approximation. Next, X2. So X2 intersection W. Okay, we don't have anything common, that means the intersection is null. So X2 is not taken as part of the upper approximation. Next is X3, X4. So this set intersection W. So we have something common. We have X4 here and X4 here. That means the intersection is not equals to null. So both X3 and X4 will come as part of this upper approximation. Next is X5, X7. So now this set intersection W, we don't have anything common. That means the intersection is equals to null. Condition fails. That means this will not be this set. This equivalent class will not be part of the upper approximation. X6 intersection W, we have common, that means the intersection is not equals to null. We have x6 here and we have x6 here, so that means x6 will be part of the upper approximation. So this is how we compute the upper approximation. And the boundary region, the definition for boundary region is very simple. It is upper approximation minus lower approximation. So if we subtract this set from this set, we are left with x3, x4. Okay, and finally the B outside region. Okay, so the definition is again very simple: U minus the upper approximation. What is U? U is the set of the universe. U is universe, that is the set of all the objects. So all the objects minus the upper approximation, we are left with x2, x5 and x7. So this is the example, and this is all about approximation. So in this class I have discussed about information system, indiscernibility and set approximations. In my next class I will discuss programming and experimentation using R language, and I'll also show computation of indecendability relations, computation of various set approximations using R.